Welcome, everyone. We're going to wait for a few more participants to join us before we get started. I see a lot of people coming in now. Okay, we have about 21 people are in. All right, I think we'll get going as other people join us. Welcome, everyone. Hello and greetings on this beautiful spring day. On behalf of the Ridgefield Library, I would like to welcome you to our program this evening. My name is Laurie McGavin Bachman, and I work in the Adult Programs Department here at the Ridgefield Library. Tonight, we are continuing our 6-part series of environmental programs via Zoom that focuses on climate change and making smart energy choices. It takes place on consecutive Mondays at 6 p.m. through May 24th. This series is co-sponsored by the Ridgefield Library and the Ridgefield Action Committee for the Environment, known as RACE. Tonight's program, the 5th in this series, is entitled Replacing Your Oil Furnace with an Air Source Heat Pump with Gavin Watson, who is passionate about reducing his carbon footprint and sharing many energy-saving measures to achieve this. You can put your questions in the chat section at the bottom of your screen anytime during the presentation. Now I'd like to hand it over to Vincent Giordano, who will introduce our guest speaker, Gavin Watson. Thank you, Vincent.
Thank you, Lori, and welcome everyone. This is our penultimate episode in the RACE's Climate Change Zoom series. For those of you who have been with us the last few meetings, thank you for continuing to join us. Every Monday evening for the past 4 weeks, a Ridgefielder and RACE member with experience and or expertise has spoken on an energy topic. RACE, the Ridgefield Action Committee for the Environment, is a volunteer group of like-minded individuals who are concerned about the state of the environment and sufficiently action-oriented to take steps to remedy matters. You're welcome to join us, and you can do so by emailing RACE Environment, that's RAC Environment @gmail.com. Tonight, we have returning is Gavin Watson. He did a series on the home energy audit, which was very well attended, and we got a lot of great questions from folks. Please put them in the chat. I will be watching the chat room for questions for Gavin. Tonight is replacing your oil furnace with an air source heat pump. Gavin recently retired from a family business in West Haven, Connecticut, and that business saved about $200,000 a year in electricity due to energy saving ideas that he and his team have implemented. Gavin, the floor is yours.
Thanks, Vincent. I'll share my screen here. You can, does that look right, Vincent?
Yes, we see your full screen now.
Cool, great. All right, so thanks for joining us tonight. I'm really excited to talk to you about this. I learned about heat pumps a few years ago, but it wasn't until I actually did some of the work putting this together for tonight that I actually realized how good they actually really are. So I'm eager to share that with you all. So one of the things you should think about with, if you're thinking about installing an air source heat pump, is how old your heating system is. So mine was about 15 years old. And from what I read, an oil furnace, oil burner, hot water heater type thing would last 15 to 20 years. So mine was getting close on the end of its life expectancy. It probably would go quite a bit longer, but I didn't feel too bad about switching out. Most people in the US spend about $2,000 or so on heating and cooling things, and heat pumps do both of those things. So I'm going to talk to you guys about heat pumps and a bit about how they work and what I did, and we're also going to get into some numbers and talk about the costs and then the carbon footprint info and that kind of thing. So we get pretty deep into it, but some pictures and things like that also. So it's not going to be all gory details of crunchy numbers, but if you like numbers, there's going to be plenty. So really old oil furnaces or old heating systems and stuff can be really bad. 50–60% efficient, but those are, I'm talking about really, really old ones. The newer ones are about 85% or so efficient. Newer gas furnaces are about 84–90% efficient. Baseboard, so electric baseboard heating is actually 100% efficient because all of the electricity is turned into heat inside your house. So they are more efficient than the other things, but heat pumps are just disobey the laws of physics almost because they're 400% efficient. And what they're really doing is they're actually just moving the heat from one place to the other. And they work just like your refrigerator does. Your refrigerator is pumping the heat from inside the refrigerator to outside the refrigerator, and the heat pump does the same thing. It can pump the heat into your house. It can pump the heat out of your house. It can go both ways, unlike your refrigerator. Your refrigerator doesn't turn into an oven. So this is a picture of mine. You can see it here, rusting away in the basement, and it was about 85% efficient. So not too bad. This chart here shows that the most efficient ones of this sort are about 88%, least efficient like around 80. So the middle of the road sort of unit. But again, getting on in years. And so the cost of replacing a unit like this is somewhere between like $4,000 to $6,000 or so to replace that, according to what I read online. So and then I just wanted to connect back to the very first one that we did with Roberta Barberi, where we talked about the fact that we have to reduce our carbon footprint on this planet and get it down to hopefully around or below 1.5 degrees Celsius. And currently, we're on this trajectory, if we don't do anything, to end up about 3.6% Celsius. So we've got a lot of work to do, but there's lots of cool things we can do. So what we're doing here is we're pulling on these two levers here, this energy efficiency lever, because heat pumps are very, very efficient, and also this electrification lever where we're getting things that were not on the electric grid onto the electric grid, because as the grid becomes more renewable, there's more renewable energy sources on the grid, it's also important to get things onto the grid. So the average household emits about 8.6 tons of CO2 a year, or 17,000 pounds or so. And your house is emitting about 70% more CO2 than your car probably does if you're an average sort of person. And you can imagine if you've got a bigger or larger than average house, it's going to be emitting significantly more than your average car would. So the houses are definitely something that we need to be thinking about. And unlike vehicles that are really, really hard to improve the efficiency on, there's a lot you can do with your houses, like we talked about with the home energy assessment audits and the insulation and that kind of thing that you can do. So, but for tonight, we're talking about heat pumps, and we're basically going to be talking about these three things here, but mostly these two. So we spend about 54% in total, either heating spaces or cooling them. So these two things are what air source heat pumps do. And then we'll also just spend a little bit of time talking about water heaters, because you can use heat pumps to heat your water too, which is another really efficient thing to do. So as I mentioned before, the Kinetico Grid right now is about 65% non-carbon. So we have a big nuclear power plant that doesn't produce much carbon into the atmosphere. So that gives us a leg up over a lot of states. And we're also in the process of installing a lot of offshore wind and solar power and other things in the state. So the Vineyard Wind project was just approved a week and a half ago. So once all those things get going, it's expected that by 2025, the electric grid in Connecticut will be powered by 91% of things that are not emitting carbon. So that's sort of the point of like, when we have something that we can shift onto the grid, whether it's a heat pump instead of an oil furnace, or an electric car instead of a fossil fuel powered car, when we do that, we're going to be dramatically reducing our carbon footprint. So this is my house. This, you'll notice, is a different colored house than the one I showed a couple of weeks ago, because we actually own two houses next door to each other. And this one here, this green one, is the one that I use as my office space. And so this is the heat pump that we installed this year on this house. And the installation it cost us $8,687 installed. And it takes care of this whole house. And the house is about 850, 900 square feet or so. And this is a mini split unit. So there's two parts here. There's this outdoor part that you're looking at here, and then there's this indoor part over here. And there's actually two of these indoor things in our house. One, we have one main room, so there's a larger one. This is that one in the main room. And then there's a smaller one in the bedroom. You can have 3 or 4 of these little subunits in your house, but in our case, we only needed 2 in this house because it's relatively small. There's really just two main rooms that we would be concerned about heating and cooling. So you'll notice too that there's these tube things on the side of the house, and they were originally white. I painted them green. I'm in the process of painting the house anyway. So I blended them in a little bit. But basically what happens is these tubes are contain the copper tubing that the refrigerant is going in. So on one side of in the unit, it's transferring heat from outside. When I'm heating the house, it's pulling heat from outside the house, sending it in, and the heat's coming out of here, out of this unit inside the house. And then when I want to cool the house, it's the opposite that happens. So that we're actually pulling heat from inside the house and pushing it out and dumping it out here. So this unit it's 2 parts connected with some tubing, and it runs both directions. We'll talk just a little bit about, if you've got central air or something like that, you can install a system like this instead of your central air. We'll talk about that a little bit, but this is the thing that I've got. I also put one of these on my garage. I'm retired. I've got a woodworking shop in the garage. I'd love to spend time out there. And I thought, well, while I'm at it, this would be really nice. So I put one on the garage, and you can see it was about $5,000 or so to do that. So I wanted to talk a little bit about the cost of this. So Vincent, are there any questions or anything yet right now?
Not at the moment, Gavin.
Okay, cool. So I wanted to talk about the cost of this because for a lot of people, this is going to be one of the main drivers. I think it really boils down to there's 3 different things that we really need to know to be able to figure that out. So, and I apologize for the complexity of this, but this is the way it goes. So the first thing we need to do is, we're buying gallons of oil, we're buying gallons of propane, we're buying gas maybe in therms, buying electricity in kilowatt hours, and we've got all these different units of measure, and we have to be able to compare them in some way. So basically what I did was standardized everything on kilowatt hours. So we're going to, converted gallons of oil to kilowatt hours of energy, and comparing everything, on an energy equivalent basis. Then what I did was looked at relative costs. So I looked at cost of the current cost right now of home heating oil, the current cost of gas, propane and electricity. And so we're going to look at that too. And then the last part of it, which you wouldn't really think of, doing most comparisons, but is the efficiency of when it gets used. So if I've got like just to exaggerate, if I've got a really old boiler and it's only 70% efficient, I might be buying fuel oil for like $2.80 a gallon, but I'm actually only getting 70% of that because 30% of it is going up the stack as waste heat. So versus other things that are more efficient may actually be less expensive just because they're more efficient. So those are the three things we're looking at. So this is so to calculate the energy equivalence of these different things, that first part that we just looked at, we could BTUs, we're going to convert BTUs to kilowatt hours. So you divide by 3,412. So 1 gallon of oil is 137,400 BTUs, right? Which that is equal to 40 kilowatt hours per gallon of oil. And then, so if you look at propane, propane's less dense from a fuel point of view. So you get less energy per gallon. So you only end up with 27 kilowatt hours per gallon of propane. If you buy natural gas in therms or in 1,000 cubic feet, you basically it's 29.3 kilowatt hours per therm. And of course, 1 kilowatt hour of electricity is 1 kilowatt hour. So the second thing we were talking about then is now we're going to take the cost per gallon. So in the case of fuel oil, $2.80 per gallon of fuel oil, that was 40 kilowatt hours per gallon from the previous slide, which then turns into 7 cents per kilowatt hour of energy. So we're converted all the energy, all of these different things into the same energy word I'm looking for, increments. Yeah. So so 7 cents per kilowatt hour of energy for oil if it's $2.80 per gallon. Propane is a bit more expensive. It's also less energy dense. So then we end up with it's going to cost us 12 cents per kilowatt hour of energy. Natural gas is way cheaper. Now, natural gas bounces up and down like crazy all over the place. So I tried to kind of pick an average number. And that ends up costing about 5 cents per kilowatt hour. And then electricity in Connecticut, again, bounces up and down quite a bit, but I picked a round number of like 20 cents per kilowatt hour for electricity. And that's the delivered cost to your meter, the generation and delivery charge both together. So now we get to the equipment efficiency part. So if I haven't lost everybody already, everybody's fallen asleep. But so here's where here's where the rubber really meets the road. So that cost of that heating oil, as you might remember from the previous slide, was 7 cents per kilowatt hour. The oil burner, I'm guessing that it's about 85% efficient, and so we're going to lose some of that. Some of that energy is going up the stack, which ends up turning into 8.3 cents actual effective heating output if we're using oil. And then you can see the number here for propane is about 13 cents. Natural gas is really cheap. It's 5.5 cents. If you've got a really good, both propane and natural gas are more efficient when you use them. You get better energy efficiency out of them. So that works out really well. If you have resistance heat, basically electric baseboard heating in your house, that's going to cost you 20 cents per kilowatt hour, and it is 100% efficient, so you're not going to lose any of that, but it's effectively costing you 20 cents. Now this is where the magic of the heat pump thing comes in here, because heat pumps are 400% efficient. So we're going to take that 20 cents, and that ends up turning out to be only 5 cents. So it's really efficient. It's in fact the most efficient choice and the least expensive choice when you go to heat your house.
So Gavin, we have a related question here.
Okay.
And it's the efficiency of the heat pump in the winter when the outside temperature is freezing or below. So this magic of the 400%, is it still 400% when the temperature is 30 degrees?
Yeah, that's an excellent question. So no, it's not. So it gets worse when it gets colder out. But on average, it's 4 times more efficient. So on those, on the days when it's less cold, it'll actually even be better than that. And on the days when it's really, really cold, yeah, it's really bad, which is where geothermal is much better, because that's going to, you're pulling from the same heat source year round. It's, 55 degrees or whatever it is, 6 feet down. And that's consistent all the time. So that's really nice from a heating or cooling point of view, but it is more expensive.
Okay, and a question back to your earlier part of the presentation when you were showing the outdoor unit and the indoor unit.
Yeah.
Are the electric wires that go to the inside unit, do they also go through those same?
Yes. Yeah,
cover?
that's a good question too. Yes, those also go through those same plastic covers that are there. Yeah, exactly. So that the coolant's going through there and the wiring goes through there too.
And it looked like the mini split that you showed was on the inside wall of a house as opposed to an outside wall. Is that correct? So the unit you're showing there above the doorway,
Yes.
is that an outside wall or an inside wall?
No, that's the inside wall. Sorry. Yeah, that's inside wall. So this is a kitchen over here. There's the refrigerator right there.
So when they installed that unit, did they have to go through sheetrock and you had needed sheetrock repair, or how?
No, so yeah, they had to. Yeah, good question. Yeah, so they had to cut a hole through the sheetrock here. This is a cathedral ceiling on this side of this wall. This wall runs down like pretty close to the center of the house. So right behind this was attic space. So they're able to run down through this attic space over that way, and that runs right to this pipe here, or this cover here with and it's coming down and going to the unit. So that's this one here. This is the one that's feeding the bedroom. Oops. I'm going all over the place. So yeah, but that's a good question. Yeah, so you kind of where you put them, you kind of got to look around and see what works for your house and the architecture and how you're going to run stuff through it. But basically, we ran the stuff through the attic space, which happened to be behind this wall. So it was a pretty straight shot up here, and then just straight down through to that attic space. And if you've got a forced air system already, we'll talk about it. But you basically can just plug this kind of system into that. So you wouldn't have to do any of this. But if you've got, oil furnace, or like this house here, this had radiant floor heating, which was very nice, very luxurious. And just the problem was that, was the boiler that was heating it. And you could do if we lived in Europe, if I was in England, they have available really nice units that will provide heat through radiant floor heating. But it's only really going to work for heating. It doesn't really work for cooling. And so this was the less expensive way to do it. And I got heating and cooling. So for me, that was the choice there.
And so one last question, then we'll let you go back to your presentation. It's
okay.
About 400%.
Yeah.
Is that average efficiency? Does it assume the typical yearly temperature variation in Connecticut?
Yeah, I don't know. So it's, yeah, I'm not sure. Because it does heating and cooling. So as you move, if we went farther north to say like Maine, then we would probably be pulling more from a heating point of view, but we'd be doing less cooling. So I think it's, I think it kind of comes out in the wash. If we move to Georgia, we'd be doing a lot more cooling and less heating. So I think it kind of evens out as long as you're using it for both.
All right, thank you, Gavin.
Yeah, you're welcome. But that is a good question. You could definitely drill down and ask somebody if you want to do this. So I just thought, graphically, I'd just show this, the relative cost. So if I use, I'm, in my house, in that house, I'm using about 500 gallons of fuel oil to heat that house, which turns out to about 17,000 kilowatt hours of energy. So, I could basically take that energy from, various different sources. And I thought it'd be useful just to show the relative cost, of of that. So if I bought, if I had electric baseboard heating, it cost me nearly $3,500. If it was propane, a little over 2,000. The oil that I was doing about 1,400. If I had access to natural gas, at those prices I was showing, then that would certainly be a pretty good deal. And then the heat pump, you can see here is about $850, and the gas was about $950 or so. So it's a good choice from a financial point of view, especially if your boiler is getting old, you need to do something about it. And of course, it's better not to wait until it does fail, and then you're rushing around and everything. So it's nicer to do something a little bit ahead of time. So this is just me guessing what the payback would be and kind of working it out. So I haven't had this for a year, but based on the kilowatt hours of energy that I would be using, I figure that the heat pump is going to cost you about $840 per year to run. So a savings about $560. The initial cost was this. If my boiler was close, I just assumed, okay, it was kind of done, even though it was only 15 years old. So new boiler would be like $4,000 to $6,000. So the difference really that I'm looking at is about $3,600 difference from replacing the furnace, the burner system that I have. So about a 6.5-year payback, which I think is pretty good. And then this information on the right, this is from an article I found online, which the numbers are pretty close to the numbers that I came up with. So I think I'm on the right track, though these numbers are more optimistic than the ones I've got. So it may actually take me less than 6.5 years, but this is me guessing. I did this guessing and then I found the article. So I thought at least it confirmed that it was kind of close. So are there any other questions so far right now about cost savings or anything like that?
Well, none yet in the chat, but a question for you is, you were showing the costs, and those were differences in fuel costs. They don't include the capital outlay. So for example.
Yes, correct.
And you touched upon that difference on the oil furnace versus the heat pump. Out of curiosity, if you were to have assumed the geothermal, and we're talking only about the fuel, we're not talking about the infrastructure costs, as John Paul and Beth were talking about. What would your inclination be about where geothermal would show up on this
on here?
chart?
Yeah, not looking at the installation cost, just where it would show up. I'm guessing probably about $600 or so. It can't be nothing. So and so this is about this bar here is about $850. So maybe half of that at best case. So maybe saving another $400 a year or something like that from a pure, dollars and cents point of view.
Okay, great. All right, so a couple questions have come in.
Okay.
Are all heat pumps the same? I've heard about cold climate heat pumps.
Yeah, good. So we'll talk about that in a little bit. So yeah, but that's a really good question. Yeah, so there are heat pumps that are better for cold climate, and there are efficiency ratings on heat pumps, and we'll talk about that a little bit.
Okay, great. Are there square foot limitations for a single unit, such that do larger houses need multiple units? You're showing one outdoor unit, for example.
Yeah. And my outdoor unit's pretty small. It's only 2 tons. So you could probably buy a 4 or 6 ton unit, use it. My house is 850 square feet. My that house is super well insulated. So it's really tight. It's like a thermostat. But you could, I think where my mind, the ground source heat pumps start to make much more sense when you get to a bigger house. That's where they may really make the best sense, because and I tried to kind of get to that last week. in some of the questions that I was asking, but you know, I am assuming that when you to get the guy to show up with the well system and get on the property and start drilling a hole, that there's a certain cost just to getting him there and getting him started and doing that, and you know, a relative fixed cost to that, and whether he drills 50 feet down or 150 feet down or 300 feet down, it makes obviously some difference, but probably not a huge amount of difference. So there may be like a certain kind of, you know, baseline cost for that when you go to a bigger house doesn't really scale up proportionally. So, but that is just more my guess.
Yeah, that's a good point, Gavin. The last question before we go to CO2 emissions
Yeah.
is, how does this apply to boilers versus furnaces? So in this example, the individual asking the question has a hot water baseboard heat. So they're
Yes.
not using, you know, air, the furnace to produce hot air. They're using the furnace to produce hot water.
Yeah. So you can do that. There are the geothermal guys do that a lot. They'll produce hot water that will run through your radiators, and the systems are getting better. So they're able to put out higher temperature water, because you know, your baseboard heating in your house, the size of the baseboard, the number of radiators you've got, and everything is all based on the assumption that the water that's going through those pipes is probably going to be 180 degrees or something like that. So if a heat pump can only get it to say 150 degrees, then you're going to end up maybe needing more radiators and that kind of thing. But there are air to water. And so the thing I showed you is a mini split unit. There are air to air heat pumps, which would go into like a furnace system with, you know, forced air kind of thing. And there are air to water heat pumps as well as water to water. So the, you know, ground source heat pump water, you know, essentially water system to pulling the heat out of that and putting it into water, running around your basement or running around your baseboard, that does exist. But they're not readily available in this country, and people don't really know much about them. But as you can imagine, with a lot of these kind of things, if you were in Scandinavia or England or something like that, it's like, yeah, there's a bunch of that stuff going on. There's a company that makes most, I think it's the largest company for heat pumps. It's called Daikin, or I think I use Daikin. It's the name of it, and they're very big in Europe, and they have, you know, lots of those kind of systems. There's really cool stuff. We don't really have much of that around here. So anyway.
Okay, thank you, Gavin.
Yeah, you're welcome. So this is the CO2 part is really, this was the thing that was like the wow for me when I put this together. So I basically have gone from 12,000 pounds of CO2 to, I will be down to 462 pounds, and actually even less than that. So I'll walk you through how that worked. So basically I was using about 500 gallons of fuel oil a year, and which basically turns into 12,000 pounds of CO2, which is pretty close to your average, you know, average home. The average home was like 17,000 pounds. So, you know, this is a small house, 12,000 pounds. That all kind of makes sense. So, and if we took that and we changed that fuel oil, you know, converted it like we did before, you know, that's 40 kilowatt hours per gallon. That's about 20,000 kilowatt hours of energy in total, but the oil burner is only 85% efficient. So a bunch of that's going up the stack. So if I'm using, so say I just threw in electric baseboard heat to replace that, I'd only need 17,000 kilowatt hours of electric baseboard heating to replace that boiler, because electric baseboard is 100% efficient. So, but now now I'm using a heat pump, which is 4 times as efficient. So now that takes me down to only 4,250 kilowatt hours of energy that I need to heat that house. So, so then the next thing I thought to myself was, okay, so what, you know, so if all of my electricity was coming from a gas-fired power plant, you know, what does that look like from a carbon footprint point of view? So, gas-fired power plants emit basically 1.2 pounds of CO2 per kilowatt hour. So this many kilowatt hours would be essentially 5,139 pounds of CO2. So, I've done it, basically more than cut this original number in half right there. But you might remember, that slide I showed with the windmills and stuff that, Connecticut's already 65% non-carbon. So just by changing out my heat pumps, changing out the oil heat for electric heat and using a heat pump, I've gone from 12,000 pounds down to 1,798 pounds, which is pretty amazing. And then by 2024, by me doing absolutely nothing, if the grid gets to 91% non-carbon sourced, then that gets me down to a measly little 462 pounds of CO2 that I'm now responsible for. So from 12,000 pounds down to 462 pounds, which I think is just incredible. Other little side benefits is no oil tank in the basement that's going to leak, or tanks under the ground, that kind of thing. And then this is, I'm taking with a grain of salt, but so I'm not 100% sure I 100% believe it, but so from what I read, natural gas leaks, and so all of the natural gas that we're using that's coming down those pipes and going to like these to the power plants and everything is leaking methane, and methane, little methane leaks all over the place on that. And those methane leaks, even though they're pretty small, they feel like in the neighborhood of 2, maybe 3% of the gas gets lost. But methane's 80 times more potent greenhouse gas than CO2. So theoretically, that's all that natural gas is responsible for 25% of the global warming, which I'm saying I'm taking that with a big grain of salt because I'm not sure I buy that. But anyway, there's some negative impact due to that. And but as the grid becomes more and more renewable, all of this kind of issue goes away. So this is just a graphical view of that. There's my pounds of CO2 that we were emitting last year. This is my heat pump if it was running on a gas-fired power plant, and this is because I'm in Connecticut, and we're 65% non-carbon on the grid, and this is what theoretically it will be in 2024. Any other questions so far?
Well,
Okay.
There is one that's about cooling costs, and it sounds like you're about ready to go into that.
Yeah.
I'll give you the question, and I have one more for you that's not on here, but it says we've discussed heating costs. What about cooling costs?
Yep.
So if you touch upon that in the upcoming section.
Yep. Yep. That's good. Yeah. Excellent segue.
I understand the last two segments here, you're saying that the payback period is about 6.5 years for this financially. So it makes financial sense.
Yes, especially if you've got an oldish, system. If you just put it in a new system, unless you're, an environmental crazy guy like me, you probably don't want to do it. But if your system's getting old, you really, really, really need to be thinking about this.
And you get significant CO2 reductions.
Yeah, huge.
Well.
Yeah.
I'd like you to touch upon what you think is the hurdle to more people putting these in. I'd be curious to know why more folks aren't just going to air source heat pump technology. So if you could touch on that, that would be great.
Sure. Yeah. I think it's just lack of, people don't know about it. Like, so I, and I consider myself a pretty plugged in guy as far as this sort of stuff is concerned. And, I knew heat pumps were good. But it wasn't until I actually put this presentation together that I was like, oh my gosh, it's just mind blowing when I started to look at these numbers, and I had no idea that it was that big a deal from a carbon point of view. And, I knew it would be good from a, financial point of view, but I didn't realize that it would be that good. So I think it's one of those, I think Bill Gates mentioned it in his book too, that there are those things that have already no extra cost to them, but it's just an awareness thing, or people getting used to it, and that sort of deal. So yeah, I think that's what it is. So anyway, heat pumps are 2 times more efficient than a window AC unit. So that's my old window AC unit. I'm giving that away. They are, yeah, so they're pretty good, pretty efficient from a cooling point of view. The other thing is that they are really quiet. I should have mentioned that earlier, but I was outside my house this morning. I got out my phone. I have a little decibel meter app on it. I measured the sound before without the unit being on, with no planes flying overhead, and background noise was 40 to 45 decibels or so of just ambient noise, birds, stuff. And then I turned it on, let it, get going and fully ramped up, and checked it again, and it was about 45 to 50 decibels. So like you could barely even tell that the thing was running. I was standing like 6 feet away from it, and they're really, really quiet. So let's see. So you'll see when if you go out to get one of these things, or you're shopping around online, there's these weird ways they have of explaining, how efficient it is. So the cooling thing is in terms of seasonal energy efficiency rating, called a SEER rating. Consumer Reports said anything between 18 and 27 is good. Mine's 18 to 20. I'll talk about that, why there's 2 numbers in a second. And then I already said they're twice as efficient as an air conditioning unit, window air conditioning unit. And then from a heating point of view, it's called the heating seasonal performance factor, because we have to have another acronym, HSPF rating. And again, Consumer Reports said 8.5 to 12.5 is good. Mine's 9 to 10.3, and it's, again, 4 times more efficient than like electric baseboard heating. So this is what the sticker looks like on the side of the unit before I took it off. And you can see it's got this range here. And so I asked the guy about that, because it's like, well, how come? Because like this is the unit on the house, and then this is the unit on the garage. So you see like this one, the cooling rating is 29.4, right? And the heating is 14. So these numbers are way bigger than this on the house. And I was like, what's with that? Because it's like the same company, everything. And so, and they're current current models and all that sort of stuff. It's like, so why is that? And he said, because this unit has more than one thing on the inside of the house, that decreases its efficiency. So the one I got, on the garage just has the 1 outdoor unit, the 1 indoor unit, and therefore it's more efficient. And the other one, I think the reason why there's this range here is because, in my case, I have 2 units on the inside of the house, but it could have 3 or 4. So I'm probably around like more closer to the 20 and the 10.3. And if you added, 2 or 3, 2 or more units on the inside, you'd probably drop down here. And I'm not sure the mechanics behind that, but I'm guessing there's, that's how it works. So we've been talking about these split units this whole time, because that's what I happen to put in. But a lot of people have forced air heating in their house. They have maybe heating and air conditioning and the same thing, and the air blowing around the house through ducting and that kind of deal. So you can do that same thing with heat pump. This is the inside unit. It probably looks a lot like the furnace or whatever that you've got in your house currently. The coils are bigger in these than they are on your typical unit, because it's got to do a lot of heating and cooling work, especially the heating part. It's gonna come off of that. So this is the outside unit, and it's going to have the same tubing connectors between this outside unit and the inside unit. And from what I've read, it looks like these kind of units are about 10% less efficient than the mini split units. The mini split units, like especially like the one that I have in my garage with just a single thing on it, are really, really efficient. These are a little bit less so, and I'm guessing because you're losing a little bit of energy just pushing the air through the ductwork, and if you've had your home energy audit, they've made sure that ductwork is really super sealed up and all that kind of thing. But still, there'll be some leakage and things like that there. So slightly less efficient.
Yeah, well, that all depends on how your ductwork was put together, right? So sometimes in older
Yes.
homes, the ductwork was actually between the 2x4s or the 2x6s.
Yeah, little
None of
tiny.
which, yeah,
Yeah.
none of which has been sealed. They just
Yeah.
use that channel. And
Right.
if that's the case, you lose a lot of efficiency.
Yeah. Yeah. That's absolutely. Yeah. Yeah. And I did look at a geothermal, so ground source heat pump for this same house that we're talking about, and I was quoted $43,000 for that. So it versus that's for a 900 square foot home versus the 8,687 for the unit that I put in, the ductless mini split air source heat pump, which is basically 1/5 of the cost of the ground source heat pump. So very first thing I did was call the guy about a ground source heat pump because I knew that would be the more efficient thing to do, and that's my inclination. But I had a little sticker shock, and I was like, "Whoa!" So anyway, so this other thing I think works fine for me. There are some rebates. So the mini split heat pump things, $500 a ton if you have electric heat in your house. That's the caveat. So I had oil heat. I don't get this $500 a ton thing, but if you happen to have electric baseboard heat and you switch, you get $500 a ton for that. And then just a plug again for the, we talked about this already, but those water heaters, again, heat pump thing, much more efficient, 4 times more efficient than, electric induction heating of your water. And besides that, you get your basement dehumidified at the same time. Or if you put it up, somewhere else in your house, you can get some cooling off of it for if you strategically locate it. And then there's federal rebates and that for those kind of things that we've talked about before. But basically, the thing will pay for itself in a year. So I'm also this is my next to last slide. I'm in the process of putting solar panels on the house.
Gavin, before you do
Yeah.
that, if you can go back to the hot water example for one moment.
Sure. Yeah. This one?
Yes. In this case, is the heat pump, is this tied to your outdoor unit to move heat to your hot water, or is that top part of the water
Yeah.
heater, the heat
Good.
pump?
Yeah. Good question. So oops, sorry. So this is the heat pump here, and it's its own separate little unit. Again, if we were living in England or Scandinavia or something, that outdoor unit would be doing all these different things, or could be doing all these different things at the same time. And like we were talking last week too, like if I want to heat hot water and I want to cool, and it's summertime and I want to cool my house, well, I'm pulling the heat from the house. I want to get rid of it somewhere. Oh, why didn't I put it into my hot water? Because now I'm doing 2 things at the same time. I'm creating hot water for my shower later while I'm cooling my house down. So you're pulling different things together, get some synergy out of it.
Okay. I think you answered one of the questions about other options other than mini split by talking about the unit you talked about earlier.
Yeah.
So I'm going to move on to, well, what happens in power outages?
Oh, yeah.
You combine that with your discussion about your conversion to solar.
Sure. Yeah. So I'm converting to solar, and I'm not adding batteries at the moment. So I'm still mulling that part over. So if I have a power outage in doo-doo, what I am leaving my oil system in place because it works. So I'm leaving it there, and I have so when we have a power outage here, I have a 2,000 watt Honda suitcase generator, little thing, and I shut off my main breaker. Probably shouldn't be telling anybody this. Plug I have an extension cord with 2 male ends, plug one into the generator, one into an outlet on the wall. And basically I can run that furnace off of that little suitcase generator. So I can, heat the house in case of a power outage that way. So that's my current plan. I also have a 12-volt battery and pump system that I've rigged up to my wells, just like you would have in a boat or an RV, so that I can, pump water out of the well, even if I've lost power, using the 12-volt battery, run it through the furnace, and we can have hot showers even though there's no electricity, and all I have is a 2,000-watt little Honda generator. So that's how we do it.
But your if you lose power, your heat pump, your air source heat pump will not be able to run.
Right, exactly. Because my little Honda generator is only 110, so it's not going to be able to do it. So what I'd have to do is once I get the solar panels on, is go for the next chunk, which would be to put in some batteries and have battery backup system, so that I could then run run the heat pump and stuff off the batteries. It probably wouldn't last a really long time if the weather's really cold, but it would last a while. Go ahead.
Something that I learned is that having put solar panels on my house and not having put a battery on, and now considering it, is that if my system was DC to DC solar panels, then you could isolate the house more easily and less expensively. Mine is a DC to AC panel system, which means I have to have 2 inverters if I want to isolate the home so it runs off of solar. So something you should think about when you think about the solar panel situation. So Generac has a pretty interesting battery backup system that also has a generator backup system. You could use, but I'm ineligible because that's a DC to DC system.
And this house that we've been talking about tonight, in this thing, it, like I was saying before, that house is super tight. When we bought it, we took it down to the studs, we spray foamed everything, and it's like a thermos bottle. So it really loses heat pretty slowly. So it it would take, and usually what I do when I know that there's a storm coming and I'm concerned that we're going to lose power, I just crank the heat up, set it for 75 or something. So if we lose power, it's going to take a long time to coast down, and that kind of thing. So get through it that way. In our other house, I got the wood stove, so that's never a problem. Just keep that going. Wood stove and candles, and I'm good. Yeah. Any other questions out there?
No, not this time.
Okay. So we must be running up on.
We have
we're getting close to the end.
Of the hour.
So should we talk about next week? You want to? So Vincent's going to be on next week. You want to give a plug for yourself? Shameless plug.
Sure. So Gavin and I are reversing roles.
Yeah.
He will be monitoring the chat function and interrupting me at inopportune times, as I have done to him. And I will be talking about electric vehicle charging. There are 2 major hurdles that people are having with electric vehicles. One is range and range anxiety, and the other is the time it takes to charge their vehicle. So hopefully we'll be able to lower some anxious people, lower the anxieties.
Okay. That's great. Oh, I had one other thing. Let me just do this again really quick. Sorry. I'm back. You can see my screen again?
Yes.
Yep.
Cool. So what is that? Uh-oh, I lost control. All right, never mind. I was gonna share a link to a YouTube video, but I'm not gonna worry about it. So there's really, if you are curious about heat pumps and stuff, there's lots of good YouTube videos explaining how they work and that kind of thing.
Thank you,
Thank
Gavin.
you. Thank you, Gavin.
you're
That was a wonderful and informative presentation.
Oh, does it? Okay, sorry.
Is everything okay?
Yeah. Sorry.
Okay. Anyway, thank you very much for our partner Race for organizing this series, portions of which can be viewed on the library's YouTube channel under the adult programs area in the environmental folder. Thank you for your lively questions tonight and for attending. We wish you a wonderful rest of your evening. Are there any other questions that you can see, Vincent?
Not at this time, Lori.
Okay, well, we wish everyone a good night. Thank you so
Thank
much.
you very much.
Thanks.
Bye.
Thanks, guys.